Hi everybody, welcome back. We are going to discuss today limits at infinity, the definition of a horizontal and vertical asymptote. So we're going to be describing what happens to the values of a function as we approach asymptotes. And there are two types. We got the horizontal, like we just said, and the vertical asymptote. So first, let's discuss what a vertical asymptote is. We define a vertical asymptote as we head towards the function as towards some c value, and if the function approaches infinity. So real simply, if I have some c value right here, and I either approach it from the left or the right, and if we're approaching either positive or negative infinity, that tells us that we have a vertical asymptote at c. So we'll call it VA. So there's a vertical asymptote at x equals c. And that's because our values are either growing without bounds or they are decreasing without bounds. So how do we take the limits or find these vertical asymptotes? There are two ways we can do this. So we're going to take a look at the easy way today. The easy way is to identify the vertical asymptote. Now you learned this in pre-cal. Remember, to find out this is you cannot divide by 0. So we just set the denominator, or the bottom of the fraction, equal to 0. So I can do that here. So I want to find out what happens as we approach 3. So if I set my bottom here equal to 0, that's going to tell me we have a vertical asymptote at 3. Now, algebraically, we can see it. If I try plugging in 3, the top becomes 1, the bottom becomes 0. Now, this is not indeterminate. It's just saying that we can even do this. So what we're looking for is what's happening as we approach 3 from the left. So this becomes asymptotic. We have an asymptotic discontinuity, which we talked about the other day. So the shortcut, pick a number close to that vertical asymptote on the correct side. Well, if you notice over here, we're trying to find the value of the limit as we approach 3 from the left-hand side right there. So what we're going to do is we're going to pick an x value close to 3 but on the left. Let's say we pick 2.9. If I think of a number line, here's 3, something to the left of it, it's going to be something between 2 and 3. I want to get as close to 3 as possible. You can actually use 2 in this case, but if you want to use 2.9, that's fine. Next, you're going to take this x value and you're going to plug this in. So, as we plug this in, we're going to take the limit as x approaches 3 from the left of 1 over x minus 3 as the following. 1 over, just plug that 2.9 in, 2.9 minus 3. And if you notice, we're going to get a positive value. In other words, this is going to be greater than 0 right there. Now, so why does this happen? Well, let's talk about a rule for us. In calculus, we say there's a rule here. If we're dividing by 0, let's say we let x get really close to 0, then this gets closer and closer to infinity. So if we're dividing by 0, we're either going to get positive or negative infinity. We just have to determine which one. So to determine which one, we can look here. Well, the top is going to be positive. The bottom is also positive. My value is approaching a positive value. Therefore, we're going to say our limit approaches positive infinity. So let's take a look at number 2 here. So if I try plugging in a 4, I am going to get my 1 over 0. So I know that this is either positive or negative infinity. We just have to pick which one. So I'm going to pick an x value very close to 4, but on the right side this time. The plus tells me I'm taking it from the right side. So I might pick 4.1. Plugging it in, I get 1 over, this becomes 4.1 minus 4 squared. All I care about is this positive or negative. I don't care about the value. And the top is going to be positive, and the bottom is positive. This is greater than 0. Therefore, our answer, again, we pick the positive infinity right there. So what is this telling us? If we are approaching the number 4, x equals 4, from the right side, this is growing without bounds. What about the left side, you might ask? Well, let's pick 3.9. Well, it really won't matter because I'm squaring it, and squaring always becomes positive. So if I approach the left side, it's also telling me it's going to start growing without bounds. And that tells us we have a vertical asymptote at 4. Number 3, well, let's try this one here. So let's say here, if I try plugging in 3, I'm going to get negative 2 on top, but 0 on bottom. So again, this is a single-sided limit, so it's either plus or minus infinity. It's going to be one of those. We just have to determine which one. So I pick a value close to 3, but on the left. So I'll let x equal 2.9. And if we plug it in, negative 2 over 2.9 minus 3. Now if you notice, the top is positive, but the top is negative. That's embarrassing. And the bottom is also negative. Two negatives become greater than 0, so it's positive. So therefore, our limit is going to be positive infinity right there. We'll come back and do cosecant in just a few minutes. Right now, though, let's take a look at 5. Now, 5 is a special case. Ready? Easy. If you notice, there is no plus or minus, which means we are talking about both sides. And the answer for this one, we're going to say D and E. And that is going to be because of at x equals 0 is a vertical asymptote. Some people will say, look, they're both going to positive infinity, but it's also okay to say that does not exist. So we like to say that the limit does not exist at a vertical asymptote. Keeps it real simple. So this is not a single-sided. Number 6 gets a little bit fun for us. We want to see what happens if we approach 3 from the left. So for this one, if I try plugging in, though, you'll notice I get 0 over 0. So this has a removable discontinuity. And that is very useful for us because I'm going to remove that discontinuity and see if it makes the problem a little bit easier. The top I can factor. Don't forget to write out your limits every time. X plus 3, x minus 3. The bottom, if I factored, it's going to become x minus 3, x minus 2. And if you notice, when we plug in the 3's here are going to cancel out. And what I'm left with is the limit as x approaches 3 from the left of x plus 3 over x minus 2. And in this case, we're kind of in luck. We don't actually have to worry about the horizontal asymptote here. If I plug in 3 on top, I get 6. Plug in 3 on bottom, I get 1. So that just is approaching 6 right there. So that's not even one of ours. See, by removing the discontinuity, it actually made it easier for us. All right, number 7. Okay. What happens as we approach negative 5 from the right? Or, let's make that a positive 5. Sorry, that should be a positive 5 right there from the right. There we go. That's much better. If we were to try substituting in right here, I would get 5 minus positive 5 minus, and then I got this quagmire right there. If I plug in the 5, the top stays 1, but the bottom becomes 0. This is our new rule. We're either going to get positive or negative infinity. So I know that this is either positive or negative, one or the other. We just have to determine which one. So my rule says I'm going to pick a number close to 5, but on the right. I'll pick 5.1. And plugging it in, I don't worry about these two. I just worry about the little fractional part. I would get 1 over 5 minus 5.1. Now, it's not much, but the top is going to be positive, but the bottom now is negative, so that's less than 0. So we're going to pick the negative infinity here. And that's going to give us 5 minus a negative infinity. Well, two negatives make a positive, So if I add them all up, we should get positive infinity for this one. So remember, we don't want to say undefined. We can say D and E on a case like number 5, but that's the exception. But all the other ones, we should have plus or minus infinity. Now with that being said, let's go back to cosecant. If I were to look at cosecant, remember for cosecant, we're really saying x cannot be 0 or any of the pi's, because that's where sine is undefined. So here's 0, here's pi, here's like negative pi right here. There's my vertical asymptote. I know what sine looks like. It goes up and then down, like so. To graph cosecant, you might remember, we're going to use the bumps and valleys. There's my cosecant, and there's my cosecant. And once I graph it, now I can look. What does cosecant look like from the right? Well, it looks like it's approaching from the right side, positive infinity. And there's our answer. From the left, negative infinity. Very simple to do. All right, go on to the next video. We'll take a look there. Okay, see you then.